In video number 4, we're going to take ionic compounds one step further. So again, this is going to build on what you learned about in video number 3. Instead of looking at ionic compounds that only contain 2 different types of elements in them, we're going to look at ionic compounds that contain more than 2 types. These are called tertiary ionic compounds. Before we do that though, my last video got cut off a little bit because I ran out of a little bit of time. So I just wanted to go back and finish that piece before we move on. So in that example, you notice that lead had 2 possible valences. It could be a 2+ or a 4+ according to our periodic table of ions. And so we need to examine what would happen when lead combines with oxygen to create a binary ionic compound. We discovered that there are 2 scenarios. We could have a 1-to-1 ratio occur between lead 2+ and O2-. 2 electrons lost means 2 gained for oxygen in a 1-to-1 fashion. Or if we had lead 4+, it means it has the ability to lose 4 electrons, but oxygen can only take in 2, so we would need 2 of those oxygens in order for all of the electrons lost from lead to be accepted by oxygen with none left over, none needed. And so you can see the chemical formulas for these 2 scenarios differ in that the number of oxygens is different. In one case it's 1, in the other case it's 2. But they do both contain lead and oxygen. And based on our naming rules from before, we would call these both lead oxide, but the problem is we can't have one name represent 2 different compounds because these 2 compounds both have physical and chemical properties that are very, very different from each other. So we need to introduce a new rule. And the new rule, according to IUPAC, which by the way stands for the International Union of Pure and Applied Chemistry. This is the governing body that tells us how things will be worldwide so we can all communicate the same language with each other. So what they decided to do is they said, well, let's put into the name an indication of which charge is being used. So you can see here, lead 2+ is used in the first scenario and lead 4+ is used in the second scenario. So what they did is they said, let's put in Roman number 2 to show this 2+ charge, and let's show a 4 here to mean that this charge is being used. Notice that these Roman numerals here have nothing to do with how many leads or how many oxygens are in the chemical formula. Instead, they are directly tied to the charge that is present on the cation in that formula. Now, for the grade 11s in University Stream, I want you to be familiar with the classical system as well because there are still bottles of chemicals used out there that use this system. This naming system was replaced by the IUPAC system. The only difference is instead of using lead 2, if you look on your ion table, you'll see that there's another name for that particular ion, and its name is plumbus. And you know from previous lessons in the course that plum is the Latin name for lead or plumbum. So plumbus oxide is the name of this particular compound, and this one is called plumbic oxide. The way this system used to work is they would use the Latin name for the particular compound, and they would use ic for the higher valence and us for the lower valence. But there were some problems with this system. You had to memorize the fact that lead could be 4+ and 2+. You had to know that, for example, the copper's 2 valences were 2+ and 1+, and then that cupric would be for the 2+, and cuprous would be for the 1+. A lot of memorizing was involved, and plus there are some metals that actually have more than 2 possible charges, and so this system didn't allow for us to be able to communicate that very well. So it has been discarded, but as I said, it still is possible out there. So grade 11s, you need to be able to use both systems, but you have your Alchem table to help you with them. All right, let's move on. Today we're going to talk a little bit about tertiary ionic compounds. And tertiary ionic compounds are those that have more than two elements in them. So we're looking at three or more. In order for it to be an ionic compound, it must have a metal and a nonmetal in it. There is one particular exception to this that I'll address in this video. And these compounds that are tertiary ionic compounds must contain something called a complex ion. You might also have heard it being called a polyatomic ion, poly meaning many atoms. Now, some characteristics of complex ions include the following. Complex ions themselves are groupings of non-metal atoms, so things on the right side of the staircase. And they have some additional electrons added into their structure. We won't study the structure of complex ions in this course, but we will in 4U. So as a result of these additional electrons being added, they have a negative overall charge. And the exception that I talked about above is a complex ion called ammonium. And it's easily identifiable because on your alchem table, it is located in the complex ion box near the very, very top as they're listed alphabetically. And you'll see that it is the only complex ion on that table that has a positive charge over on it. It's the only positive complex ion. And it contains no metal ions either. So that's the only exception I'm referring to. Otherwise, complex ions often have oxygen in them. If you look at your alchem table and the complex ions that are listed there, you'll see many of them have oxygen in them to some degree. You'll notice that if you look at their names often end in ATE or ITE, and so that makes them identifiable in an English sense as a complex ion as opposed to the IDE endings we've been using for binary ionic compounds. And as I said, the other big plus about the alchem periodic table that we use is that they're all listed there for you. So there's no memorizing required. Memorizing, of course, makes you able to complete questions faster, but you just need to be resourceful and know how to find them. And as I mentioned earlier, they are all listed in that box in alphabetical order, which assists in helping you find them. So I'd like to show you how this works. We're going to go from the IUPAC name of a chemical that has a polyatomic ion in it and come up with its formula, but then we're also going to work the other way too and say, here's a chemical formula, it contains a complex ion, what is its name? So let's model a few examples for you. Have your alchem periodic table of ions handy to assist you with this. So when we see the word sodium and we're on the ion side, we see that sodium can be represented by the formula Na1 plus. And when we see carbonate, we notice this ATE ending and we go, must be a complex ion. Let's look in the complex ion box and you'll see in the first column that carbonate, about 2/3 of the way down, has a formula of CO3 2 negative. So it has one carbon, 3 oxygens, all bonded together with a couple of extra electrons in there too. Now, let's remember that Na1 plus means that one electron can be lost by sodium. And CO3 2 minus means it has the ability to take on 2 electrons. So how many sodiums will be required for carbonate to do that? Well, 1 isn't going to be enough. We're going to need 2 sodiums instead. So 2 sodiums would be able to lose 2 electrons for a total charge of 2 plus, and a carbonate has an overall charge of 2 minus, so the 2 plus charge overall and the 2 minus charge overall come out to being neutral. And then we have to have these things combined together in neutral ratios. And so the chemical formula for sodium carbonate would be Na2CO3. While you're learning this, if you want to include your charges at the top to help you think about things, and remember this 2 plus charge applies to the whole thing, not just the oxygen part. Okay, the whole thing is 2 minus. So 2 1 pluses is 2 plus, 1 2 minuses is 2 minus. Those equal each other. Let's look at another example. Magnesium hydroxide. So on the ion side, we see that magnesium has a Lewis symbol of Mg2 plus. And we see this word hydroxide and we think right away, let's look on the non-metal side of the ion side of your periodic table. However, when you look on that right side of the staircase and you skim and scan, you don't see hydroxide listed there anywhere because hydroxide is not an element. And so your plan B, when that doesn't happen, is you need to go to the complex ion box. And of course, nothing is perfect, but there are a couple of complex ions in there that do end in IDE. And I would encourage you to take a moment to identify them so that you're aware that that can possibly happen. Now, if you look in the second column about 2/3 of the way down, you'll see that hydroxide is there and that it has a chemical formula of OH1-. So again, this 1- applies to this entire thing, not just to the H portion. So let's think about this. Magnesium has the ability to lose 2 electrons. If they want to come over here to hydroxide, as soon as one of them does, it would be full. But there's still another electron to account for. So we must need 2 hydroxides to satisfy magnesium's desire to lose 2 electrons. So let's illustrate that by writing a chemical formula that has a ratio of 1 magnesiums to 2 hydroxides. However, why bother writing hydroxide twice? Instead, let's do this. Let's write Mg and let's put in brackets OH, but because we need 2 of them, let's put a 2 on the outside of that bracket. So it applies to the entire thing. If we only wrote OH with a 2 like this, the 2 would only apply to hydrogen, not to oxygen as well. By bracketing it, now it applies to both of them. 2 hydroxides are needed. So the chemical formula for magnesium hydroxide would be Mg bracket OH taken twice. Let's do one more example with that exceptional complex ion I was telling you about, ammonium. So ammonium is not a metal. That's where you would look first. You're noticing we're writing the metals first and the non-metals, or the second, or the cations first and the anions second, always, 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 to be consistent. So ammonium, since it's not a metal, must be in the complex ion box. And lo and behold, second one down, you see NH4 1+, the only positive complex ion that we're going to use in the scope of this course. Now phosphate, again, you see this ATE ending, which is your clue that it might be in the complex ion box. And lo and behold, it is. If you look in the third column, a little bit of the way down, you see that phosphate is PO4 3-. So this means that NH4 1+ has the ability to give away an electron because it has a charge of 1+, but phosphate has to accept 3. So if we do a transfer of just 1 electron, that's not going to satisfy phosphate at all. Instead, we're going to need 3 of these ammoniums in order for phosphate to gain its 3 electrons that it needs. So how can we communicate that? Well, if we want to have 3 phosphates, well then let's have 3 ammoniums, then let's have 3 ammoniums. So let's bracket the ammonium and put a 3 on the outside so that it applies to that entire bundle. And then let's have 1 of these phosphates here. And you'll see that overall the charge is equal. 3 1+ is 3+, 1 3- is 3- overall. And that would be the chemical formula for ammonium phosphate. Now, for tin oxalate and oxalate together, we notice that tin on the ion side is one of those that can have multiple valences. So if all you're told is that something's called tin oxalate, well, it could be one of 2 possible compounds. So tin is element number 50. And if you look, you see that tin can be a charge of 2+, but it could also be a charge of 4+. Now here's our ATE ending here. Let's look it up in the complex ion section. And lo and behold, oxalate's chemical formula is a really cool one. It's OOCCOO, and it has a charge of 2-. Now because these two are equal, they would combine together in a 1-to-1 ratio. And we could just leave the chemical formula like that. No subscripts here implies that they are 1s. But over here, if we put tin 4+ with oxalate, we notice that they're not going to combine together in a 1-to-1 ratio. Instead, we're going to need 2 oxalates in order to allow that tin to lose its 4 electrons. And that would be the chemical formula of it. We would call this first one tin 2 oxalate, and we would call this second one tin 4 oxalate, using Roman numerals for the 2 and 4 respectively. Now, going the other way, if you're given the formula and you have to come up with the name, first thing you have to do is you have to say, you know what, let's divide it between the cation and the anion. And the cation is almost always just the first element. The only exception, of course, is when that first part is ammonium. So we split it here and we say, let's name the positive part and let's name the negative part. Well, the positive part here is potassium. And if you use the alchem table, you can see the other part is called sulfate. And similarly down here, we have aluminum. It can only have one charge, and the other part is nitrate.